Hi guys! So problem 12 from the pre-calc test asks us to match some expressions to some graphs. And what they're mostly looking for here is to see if you understand how graphs are translated. And translated means they're slid around or they're flipped around from their generic form. So here we're dealing with, excuse me, these should all have squares. Squared, squared, squared. Here we're originally dealing with a parabola, x squared. We'll say, y equals each of these, since we're dealing with x and y axes. So if we're normally dealing with y equals x squared, let's just remind ourselves what that looks like. That looks like this. Same parabolic curve as all the functions up here. And the question arises, how are these values transforming or translating our original graph here? So what we're looking at is these graphs and these functions. And let's first consider what happens when we add or subtract this number 18 to the outside of our square function. If you'll notice, if this is the square function, everything inside the parentheses is inside the square function. So this 18 outside of the square function can't do anything to our x values. But you'll notice that if normally y equals 0 when whatever is in here is equal to 0, then if you add a negative 18 to the outside, all of a sudden, when everything on the inside is equal to 0, which is at that central, apex point, then all of a sudden this is actually equal to negative 18, which means that our entire graph has been shifted downwards. So let's look for all the graphs that have an apex point of height negative 18. So this one's down there, and this one's down there, and this one's down there. So I'm just going to put a red dot next to all three of those. Red dot, and a red dot for this equation here. Now, what's the next thing we can look at to narrow down our possibilities? Well, what happens when we have a negative value outside of the function? If we put, just in front of our generic equation, y equals negative x squared, that would cause any value that was normally positive to become negative with respect to the y-axis. For example, at x equals 1, we normally have y equals 1 as well. But if we have the function y equals negative x squared, then when we plug in 1, we end up with negative 1 for the y value, which is down here. And the whole graph looks like this. So what does that tell us? That tells us that our graph should be pointing downwards. So how many of the graphs that we've selected as options are pointing downwards? Well, just these two. So let's get rid of that. That's no longer an option. And then let's look at this 12 here. What does this 12 mean? Well, this 12 is inside the square function. So let's think about if we had this squared function and we wanted to find the apex point, right, where y is equal to 0. If we're looking at without any sort of additional shift up or down, then when y is equal to 0, this inside stuff has to be equal to 0. But if it's x plus 3, then how do we make x plus 3 equal 0? Well, we have to plug in a negative 3 for x instead of a 0, which means that everything on the graph, which used to be over here, has now shifted over. So we moved x to negative 3, the graph moves over here. And as you can see, everything has shifted in the negative direction from what this number indicates. Which means that if we have a positive 12 here, that means we've shifted our apex point to have a value of x equals negative 12. So this one has shifted to the right. It's shifted to with an apex point at positive 12. And this one's shifted to the left with a negative 12. So this is the one that we want. That's the answer to this first equation. It has a function that looks like this. Now we can apply these same strategies of mind to the next few equations. Let's look at this equation. Let's label it a blue one. So we'll draw a blue box around the equation that we decide correctly matches this one. Well, I don't see any negative sign out front, so that leads me to believe that this should be pointing upwards because we haven't given it that negative flip. So if we're looking for anything that points upwards, that's going to include this guy, and this guy, and this guy, and that's it. One of these three is going to be our choice. And then it shifts up to a positive 18. So this one shifts down to a negative 18, so it can't be that one. And this one goes up, the apex point goes up, so there's the 18, and this one also goes up. So these two are still possible options. And then let's see what this 12 does. Well, it's a positive 12, which, if we remember, let's just review that one more time. So if we've got a function and the apex point is usually at 0, if we have instead x plus 12, then how do we end up with a y equals 0? Well, we have to plug in a negative 12 here. So that means that our function, if we add 12 to the inside, has to scoot over to the left by 12. So which one of these has been scooted to the left? This one looks like it's been scooted to the right, and this one has been scooted to the left. So this is our final answer for the second equation. Let's put a square around that as well. Nice blue square. And finally, let's label this one green, and let's figure out which graph represents this function. Well, it's got a negative outside of the squared function, which means that it's got to be flipped. It's pointing downwards, so this is an option, and this is an option. And let's see, that one, this one's also an option right here. And let's see here. It's also got a plus 18, so it has to be shifted upwards. This one's shifted upwards, and these two are both shifted downwards. So this has to be our choice for the third equation. This one's our choice. He's sort of hiding underneath the red function. And now allow me to point out one just fun little idea, which is reflections. So as you noticed before when we were talking about just the generic y equals x function, if it was pointing up like this normally and then we rewrote it to be y equals negative x squared, that would be pointing downwards. Because anytime you plugged in the same number for x, like say this value, if normally it was up here, then it would be equally but oppositely down there in this function. So is one of these symmetric to the other with respect to the x-axis? Which is to say, is any of these a reflection of another one of these functions? The answer is yes. If you'll notice, the blue function and the red function look like mirror images of each other. If we drew the red function over in this graph, it would look like it was down here, which is opposite with respect to the x-axis. It's a reflection over the x-axis. And there's also a way to confirm that in the function itself, in the written version. If we wrote this out, it's negative x plus 12 squared minus 18 equals y. But notice that you can factor out this negative, and you end up with negative x plus 12 squared plus 18. And that can be directly replaced by this blue y. Notice that it's exactly the same. It's x plus 12 squared plus 18. Here it is again. X plus 12 squared plus 18. So the fact that these two are a reflection of each other is reflected not only in the graph, but also in the written expression.